Okay, that is the forward pass. Okay, with the purpose of forward pass, because we want to find the y1 hit and y2 hit, which is the predicted output. Once you know the y1 hit and y2 hits, then you can compute again the E1 and E2, which is the error happens there. The error or the cost function or the cost value happen at that particular points there. And then from once you compute the E1 and E2, then you can get the cost function or the total error, which is the E is equal to E1 plus E2. So now again, remember that our objective, we want to find the del E over del W or del E over del B. That is the purpose we compute this one, because that is the gradient descent step in order for you to find the optimized W and B that can provide the minimum value of cost function or the minimum error that can represent by this artificial neural network given the training data set, or in other words, to find the best fit model that can fit into your training data. Then you need to compute a gradient descent, and then in gradient descent, the objective is you want to find the gradient itself. Okay, the gradient itself. So because the gradient will determine how much you need to tune your W and your B to going towards finding the minimum cost function value or the minimum errors there. So remember that we want to compute this one, del E del W, and we want to find this one, del E and del B. If okay, here in this case we have W and B, so that's why we need to find this one or this one. So in order to find this one and this one, once you already compute the fast forward, you already know the E there. Now we need to compute the backward pass mechanism. So the backpropagation, when I said the backpropagation, is actually both step, which is forward pass, backward pass, forward pass, backward pass. So you will do this iteratively to find the optimum W and B. So now we just finished the forward pass. Now I would like to discuss about what happens to the backward pass, and again the purpose of backward pass, because you want to find this one, del E del W, del E del B. Okay, so just from this, because we have a lot of W and B, okay, of course I cannot show you all example, all thing derived from here to here. So I just take one cases there. We talk about this one first, because now it's a backward pass. When we talk about backward pass, it must start at the last layer towards to the input layer there. From the output layer towards, means that the backward pass should be into that direction. So that's why we start from this layer. Okay, but if you see in the forward pass, because there is going toward that direction, that's why we start at this layer, the input layer. So at the backward pass, from here, let's consider only one W. Okay, consider only one W, which is W35. So we want to know how much a change in W35 affect the total error. So this is again, this is why we want to find, or our objective is why we want to find the del E over del W35, is because that is represent how much a change of W35 affect this total error. So means that how much this W contribute towards this error. Okay, of course it's not just this W. You will need to find all del E del W, del E del WY35, del E del W45, del E del B5, and so on, each and every W and B over here. So what is the meaning by del E del W35 is actually is the total change that make this error happens. So or in other words, how much the contribution of this W35 towards providing or resulting this error. So that's why we need to find the DelE of over the del W35. Okay, there's a little bit wrong in this statement there. This is not also known. Okay, just delete this part. Just delete this part in your notes. Actually, it's not also known as a this one is actually is a updater. It's not a DelE del. It's not like this. It's not similar to this one. Okay, later you see that what is the meaning by that that delta rule. This is called a delta rule there. Or this one is actually is an updater of your W35 updater. Okay, it's a this updater of W35. I will explain later what is the meaning by this. Actually, it's a delta rules updater. There is a updater for your wake 35. Okay, this is another name for your DelE del W3. Is a partial derivative of E with respect to W35. Of course, this is a partial derivative with respect to of the error functions there with respect to your W35, and this is also known as a gradient. Again, this is a gradient. The gradient with respect to W35. Of course, the gradient itself is a slope, which when you count the slope value is actually how much change. Okay, in other words, the slope is also known as a represent how much change of that point with respect to this function E there, or the cost functions there. So that's why we need to find, or why we want to find this del E over del W. Doesn't matter which W you want. Okay, and then of course, in order to derive or to find this expression, you need to know the change rules. Again, same as the previous lecture regarding the linear methods, where in order for you to find each and every derivative there, del E del W, you need to use the change rule to express that from the input layer value, input layer value E there, through each and every B and W that exists. Doesn't matter is it from the output layer or the hidden layers there. Okay, so this is the updater there that I mentioned before. It's not similar. Your updater should equal to alpha del E over del W35. Actually, this is the updater. Just remember that. Okay, if you remember that, why because during the gradient descent, remember that I just write the updating process of your W and your B based on gradient descent. You need to find your new W should equal to your current W minus delta. I'm sorry, it's not delta. This one is updater. Updater of your wake W35. Okay, so here this one is equal to alpha, which is your learning rates, and your the change with respect to the error functions there, which is also known as your gradients. So that is why they call this process there is as a gradient descent. Okay, because this one is based on the gradients, but of course it's not a totally gradient. It should be have one variables there called alpha, which is your learning rates. Of course, if you want to make sure this updater equal to your gradient, then you can set your learning rates equal to 1. If this is equal to 1, then this one is equal to this one. But normally we will tune this one from 0 to 1, means that sometimes we don't want to have fully gradient value update your W35, because it will make your step more bigger and you cannot find the minimum, the global minimums there. That's why this one you need to have the value which is from 0 to 1, and in most of the time you will give the value which is very small, 0.0 something, so it will make the learning process slower, because the number, the distance of the step is very small to going towards the minimum value. Okay, so that is the updater. Okay, this one is the updater. The updater of your W35 is represented by this triangle W35 updater. So if this is the updater, and again this is this one, it doesn't matter, this one is you need to set by yourself the alpha learning rates. Now we want to find this one. Now because this one have been set, it one is fixed, means that it is already there, the value. In order to obtain this updater, you need to know this one. And again, that's why our main objective is we want to find this gradient, because we want to find the updater. Okay, so how do you express this one? This one, if you extend from the previous slide there, how to find that one? You can express in this way: del E over del W35 is equal to del E over del Y1 hit, then multiply with del Y hit 1 over I'm sorry, this should be net there, forget to put there, it should be del net. Okay, del net 5 and del net 5 here. Okay, this one is again, this is what we call as a change rules. Okay, so in this model, artificial neural network, you will use a lot of change rule as compared to the previous one, because we have a multiple stages of neuron, or multiple stages of logistic regression, or linear regression, which is stacked together or cascade together. So that's why there's a lot of change rule to do this, as because you have, if you increase more and more neuron, you will increase more and more linear regression or logistic regression inside your network. So that's why the change rule will become longer and longer to find, or to find or to obtain this del E over del W, whatever W you want to find there. Okay, if you go back here, okay, to find del E, okay, again we want to find at this position. Okay, this position there, del E over del W 35. So from here, this is the expression. Of course, the total errors there, you must this one plus this one. Okay, here you remember that we have here, there's a net there. This one is net 5. This one is your Y05. So of course we have the activation function there. So to find del E over del W35, because E here is come from here, okay, it's come from here. Now del E must over what? What is the independence variable of E? E should be Y1 hit there and Y2 hit. If you remember, actually your E there consists of this it's depend on two variables, which is y1 hit and y2 hit. Okay, because if you plus E1 and E2, this one contain y1, you can see here, and E2 contain this one. So that's why this function is depending on this one. So that's why to find this delta here, then you need to extend the change rule into del E over del y1 hit. Okay, why we need to find this one over with respect to del y1 hit? Because we know that our E have two independent variables, y1 hit and y2 hit. So now we want to process the W35, which is only involved in finding this node or this neuron, and this neuron will provide only y1 hit there. Okay, however, and y2 hit only produced by this part, this direction. Okay, so means that there's no relation between this W35 and y2, but there's a relation between this W35 and y1 hit, because to find y1 hit you need to know the W35, but to find the W2 hit you don't have to know the W35, because W35 is here. W2 hit is only depend on B36 and W36 and W346, which is this one. So that's why we only do a partial derivative of del E over del y1 hit. Okay, that's the reason why we start our change rules like that, because when we see the pictures, to find the del E over del W35, we must start at del E, where del E is this location, because E is our at this location, and you see that E is depend on two variables, which is y hit 1 and y hit 2. But to find the W35, you only need a W1 hit, because this one to produce y1 hit you only need W35, and W2 hit here does not have relation with W35, because to find W2 hit you only need this one and this one. Okay, I hope you can clear about that, how actually we define and how actually we start our change rule to do that. Once you know this one, then still you need to extend your change rule. Of course, at the numerator there, still you need to follow the denominator of the previous one. So that's why I follow del y1 hit over what. So now it's over what. So and then you know that what is y. Y is 05, and 05 is a output from the activation function f there. Okay, so this is activation function. Okay, I just explained here. Here. So y here is come from your activation function. Okay, during the forward pass we compute these two. One is input function, another one is activation function. So we know that our y is depend on net, because to find y hit 1 there, you need to compute the activation function f, where the input is net. So that's why then you can continue expressing this thing with del y1 hit over del net 5. So why? Because this is already there. There's a function there during our past forward pass. We already know this one. This is the definition of your y head, y1 head. Okay, that's why you can easily find this one. Okay, so it's easy to find this one because you already have the equations there. Okay, now of course the numerator there, the numerator of another DelE there should be DelE net 5, and then the denominators there should end up with your W DelE W35. Okay, of course now because this one and this one is already end up together to produce your DelE over DelE W35. Now means that now is it this one possible to obtain? Yes, it's possible because this expression can be obtained from the input function. When you compute the input function of your net 5, this is the expression. So now if I want to have this one, which is DelE net 5 over DelE W35, I can obtain from this function. Okay, so that's why in order for you to find DelE over DelE W35, you can express it or define it in this change rule where you have three components there: DelE del y1 head, del y1 1 over DelE net 5 multiply with DelE net 3 over the DelE W35, and then from there you need to find one by one what is DelE net 5 DelE W35, which is this one. So this one is actually this one you derive with respect to W35, means that you will cancel this one, you will cancel this one because it's a constant, it's not a variables. The one that consists of variable is only this component. So derivation of DelE net over DelE 35, this one become 1, so that's why you have 0, 3, which is this one. Okay, so that is for this component only. How about this component? So of course this one is depends on this one. Okay, this one. So to find DelE y head 1 over DelE net 5, then you need to know the activation function. So since we don't set yet what is our activation function, is it a sigmoid, is it a sinc function, or is it a unit step function, then we just use a variable f apostrophe to represent the derivative of our f, means that the df over the let's say this is your function f, then if I talk about del f over del x, then I just replace with the symbol f apostrophe. So that's why I use here as a apostrophe there, because that's meaning it's a derivative of this activation function over the net 5. It is same things there. Just put it first, later we, because at the end later we can set what type of activation function you want, and then once you know the activation function that you want, then you just can simply replace that notation by do the derivative of that functions. And then the third component, which is this one, del E over del y 1 head there. So this one is come from the definitions there. Remember that my E totals there, again my E total is equal to 1 over 2 y sorry, what is the, yep, y1 minus y1 head square plus 1 over 2 y2 minus y2 head square. So this is E1 and this is your E2. So if you want to compute the del E over del Y1 heat, then of course this everything here is a constant, that's why they become 0, and then you just need to do derivative of this component only. So if you compute this one, then what you get is this one. Okay, so now in order for you, again our objective, if we want to find del E over del W35, so now our del E or our del E or over our del W35 can be computed as and can be expressed as this one. Okay, so that is happened at W35. So then you need to repeat the same process to find other parameter which involved at this output layer, including the W45. It means that you need to find del E over del 45, del E over W36, del E over del W46, del E over del B6, and del E over del B5.